Just came back from campus. Okay, let's finish this chapter with an example. So let's suppose that we have a vector value function. R of t is given by the following. Is t times I plus t squared times j. Plus 0k. Okay. And t here is any real number, the whole line. Okay. So this is given. Now we are going to find the curvature. And then we are going to find the unit normal vector. The binormal vector. Okay. And then we are also interested in the normal plane. And finally, the osculating plane. To the graph of the function. At a certain point, let's say the origin. Okay. And then you can see everything. Okay. The pictures behind all these concepts. So here is the way to do it. If you remember, if you have a vector valued function on an interval. Okay. And suppose that this is the curve. And then we have something like this. We are interested in the point of t. And the way we study it is to look at the unit tangent vector. Which we call T of t. And then we are going to look at T prime of t, the derivative of the unit tangent vector, which is perpendicular to T of t. And then we'll normalize it. We call this n of t. N of t is perpendicular to T of t. T of t and N of t determines a plane. And then we look at a vector perpendicular to the plane determined by t and n. And we call that B of t, the binomial. Right? I have skipped the curvature in this discussion. Okay. So we have a plane, a three-dimensional coordinate system moving along the curve. But this is too abstract. Okay. So we are going to specialize to our example. R. So let's look at the solution to the example. Now, we know that R of t has a formula associated with it. Let's denote the first component by x of t. That's equal to t. Y of t is t squared. Z of t is equal to 0. Okay? Now, can you figure out what the graph of R of t is? What is it?
Well, the z will for sure be 0. So then it's just so the graph will just be t plus t squared, I believe.
Well, your first remark is correct. Z is always equal to 0, no matter what it is. We are on the xy plane, correct? No matter what t is, Z is 0. So we are on the xy plane. On the xy plane, y is equal to x squared. So what is it?
Parabola.
Parabola. Okay. So instead of trying to put the x, y, z in this way, I am going to write it differently. I put the x-axis like this, and the y-axis, and then the z-axis is going out of the board by the right-hand rule. You know that, right? So the z-axis is coming out of the board. So I don't need this one. And I also don't need this one. But it doesn't matter too much. So this is the z-axis. We use the right-hand rule. Put the rim of your palm along the x-axis, turn it to the y-axis, and your thumb would point out of the board. That's the right-hand rule that people use. Okay. You may ask, why don't we use the left-hand rule? Well, anyway, tradition has been dominating. So we are going to get a parabola. strictly on the xy plane, which is a curve in three-dimensional space. Okay, not bad. Now I am going to look at the origin. The point of interest. You can look at some other points also. Okay. So what is the unit tangent vector? The unit tangent vector is given by the derivative of the vector value function. So it's the derivative of t, which is 1, the derivative of t squared, which is 2t, and the third component.
Sir,
Yeah.
so just to clarify, you're using the t of t equals the derivative of RT over the magnitude of the derivative of RT?
Well, I am just differentiating at this point. I haven't normalized it yet.
Okay.
Now I am going to normalize it. This is R prime of t. Right?
Okay. Yeah, that's what I was asking, sir.
Yeah.
Thank you.
And then I am going to divide it by its norm. And what is it? It's 1 plus 4t squared. Okay, so t of t is 1 over the square root of 1 plus 4t squared. And then 2t over the square root of 1 plus 4t squared. And then 0. This is the unit tangent vector. At any point on the parabola. So let me take this away first. Now, let's try to find the curvature. Now there are many formulas for the curvature. I am going to use the simplest one. So kappa of t is equal to the norm of, or the magnitude, or the length of the derivative of the unit tangent vector over the length of the vector value function, the length of the derivative of the vector value function. Correct? Ah. So let's try to calculate the derivative of the unit tangent vector. It's a bit tedious, but it's not difficult. So I am going to differentiate T of T. Okay. So what am I going to get? So I am going to get 1 plus 4t squared. To the power minus 1/2 minus 1 which is minus 3/2. And then I have to differentiate this, which is ht. Right? I hope it's right. 1 plus 4t squared to the power minus 1/2 minus 1, which is minus 3/2. And then you have to differentiate 4t squared. Yeah.
So times minus 1/2, right? So to the quantity you just made, we have to multiply by minus 1/2.
Yeah, because I bring this up, minus 1/2. So, thank you. So I should have this. I hope my notes is correct. Yeah, my notes is correct. Next, I am going to look at this, which is a little bit more tedious. I use the quotient rule. So I take the denominator and then I differentiate the numerator. So I have 2 times the square root of 1 plus 4t squared. Minus 2t. Oh, I don't have enough space to that. Minus 2t. Times the derivative of this one, which is 1/2. So I write it here. And then 1 plus 4t squared. And then I have 1/2 minus 1. So it's minus 1/2. And then I have this one, which is ht. So I am going to have 4t. That's the second entry. It's not very good, but
So the power part, isn't that should be -3/2, same as,
okay, let's check it. Take the denominator. Okay. And then I differentiate the numerator, which is 2. So
I feel like that should be 2 over square root of 1 plus 4t squared.
and then the whole thing is divided by the square of the denominator, which is 1 plus 4t squared.
Oh, sorry, sir. Oh, you were doing the other way. Okay.
Okay, that's the quotient rule. I'm using the quotient rule. That's the second answer. Sorry about that anyway. And finally, the last one is easy, is 0. Okay, that's t prime of t. It's in the notes anyway. I will post it. So it's correct. Okay. We have r prime of t. What's r prime of t? That's easy. I think we did it before. The first one is 1 to t
Sir,
and 0. Yes.
just a clarification. So the derivative of the tangent at t, so it's -3/2, right? So 4t times 1 plus 4t squared times -3/2.
Which one are you talking about? Which entry?
So I'm talking about how you use the quotient rule. So minus
the quotient rule is this: take the denominator, you differentiate the numerator. That's it.
yeah.
And then
I know.
let me finish.
Okay, sorry.
And then I subtract the numerator. Okay. And then I differentiate the denominator, which is 1/2 to the 1 plus 4t squared to the power minus 1/2. And then I have ht coming out, but I have 1/2, so it's 4t. And
Sir,
then I take the denominator square.
But sir, shouldn't it be -3/2?
Why -3/2?
Because when you do the derivative of 1 plus 4t squared to the power of 1/2, the 1/2 gets down, and then 1/2 minus 1.
This one is the denominator. I differentiate the denominator, so it's 1/2 minus 1. All right.
Yeah, I know, but sir, I'm talking about both the exponent. It says -1/2. Shouldn't it be -3/2?
No.
No,
This
okay.
one is -3/2. What do you get when you differentiate this?
So you get 1/2 times 1 plus 4t squared to the power of -3/2.
Negative. It's 1/2. I'm not bringing this up there. The denominator is this.
Okay.
Okay?
Yeah.
It's 1/2 minus 1.
All right.
Okay? So it's correct. This one is -3/2. Okay? Because you bring this up, it becomes 1 plus 4t squared to the power minus 1/2. But here I am not going to bring this out. It's going to be minus the numerator times the derivative of the denominator.
Yeah, I did the subtraction wrong. Sorry, sir.
Okay. So I don't need this anymore, I guess. Now, I am going to look at the following. So what am I going to get? So I am going to look at the curvature at 0 because I want to look at the curvature at the origin. And the origin corresponds to t equal to 0. So kappa of 0 is the norm of t prime 0 over r prime 0. Okay, what is the norm of t prime at 0? So this is 0. I have 2 here. And then this is 2t times 4t times this whole thing, which is also 0. So I have 0, 2, 0. So what is its length? Its length is going to be 2. What about this one? The length of r prime 0. So I put 0 here. I have 1, 0, 0. And its length is equal to 1. So the curvature at the origin is equal to 2 and is not equal to 0. Okay. Now, note what I have done. I differentiate first and then plug 0 in. If you do it the other way, you got the wrong answer. Okay, that's very important.
Professor,
Yes.
I have a stupid question. So when we calculate the length of vector, we don't square it.
Well, what's the length of the
So-
vector?
So length of the t prime of 0, we don't square.
This is 0, 2, 0. And then you square it, which
So
is 4.
square root of 0 plus 4 plus 0 is 2. Oh, you already did. Sorry.
Okay. Oh, well, you can see it from from the vector.
Yeah, the square and the
Thank
square
you.
root cancel out.
Yeah. Okay. So that's the kappa. Let me keep this. What's the next thing that we need to do? We have to find the unit normal vector, which is n of t. At 0. Okay. And what is it? Is the tangent vector differentiated and evaluate as zero. Over is normal. Right? That's the unit normal. That's how we define it in differential geometry. Okay, so T prime at 0 is 0 to 0. Over is length, is magnitude. Its magnitude is 2. So you divide a vector by its length, which is going to be 0, 1, 0. It's a unit vector. It's actually J. Right? Very nice. So this is the unit normal vector. Okay. Now, what about the binorm?
Sir,
Yes.
so what would you say for your therefore statement for n at 0? So therefore the unit normal at t equals 0 is just the y vector or the j vector? Okay.
It's the J vector. Right?
Pardon me?
This is the J vector,
Yeah.
right?
Okay.
Okay.
So we can just say the unit normal at t equals 0 is the j vector.
Yeah.
Okay.
Or
Thanks.
you can put this down. It's up to you. It's
Okay.
too nice to put it like this.
Yeah. Okay.
Okay.
Thanks, sir.
Okay. Keep that in mind. We need it. Now, what about the binormal? Next. I am going to find the binormal vector B. What is the binormal vector? It's the vector perpendicular to both T and N. All right? And how can we find a vector perpendicular?
Is it cross T prime 0 cross product with N prime 0?
No. How do we define the binormal?
Is it the cross product of the unit tangent vector and the normal
Yeah.
vector?
That's why I drew the picture at the beginning. So it's a cross product. And the order is important. Well, maybe not that important. You just get minus. Okay. But conventional, it's better to respect the order. Otherwise, you get a negative. So it's the cross product of T with N. Okay. We can put 0 here. So I'm not going to put down the t, okay? So at the origin, we are going to have the cross product. And it's best to compute the cross product using the determinant. Well, actually, many people or many professional mathematicians don't like the determinant. There is a book in linear algebra titled Down with Determinants. But in fact, the determinant is very important. It comes up everywhere. Is the determinant of the following matrix? It's always like this for vectors in R3. So you put ijk, and then you put t in the second row. What is t? Unfortunately, I have erased it. What is t? Now let me,
T of 0 is 1 0 0.
1 0 0. No,
It is right.
t is the derivative 1 to t, and then 0. Yeah, at the origin. Is 1 0 0. Yeah. Okay. And then finally, I have to take the unit normal, which I can remember because it's J. Right? So we got this. Now, to compute this, I pull the first two columns out. And then I multiply like this. So I have k. And then I multiply in the reverse order and subtract. But they are all zero. So we only have k. That's the binomial vector. Okay.
So sir, so just to clarify, you got 0, 0, 1, and then that's just the k vector?
Yeah.
Okay,
Along the same axis.
all right.
So we have z axis here, x axis here, y axis here. And we have a parabola. And then at the origin, we have found the unit normal, which is n. And we know that is j. This is n, okay? And then we have the binormal, which is k, is the unit vector along the z-axis. So this is k. Okay, and this is b. B of t. But at the origin, we simply skip the independent variable. So you see, they are perpendicular. Now we are going to find the unit normal plane or the normal plane. How do you find it? How do you find a plane? Okay. You want to find a plane perpendicular to n. Right? So how do you do it?
P cross n is the normal vector of the normal plane. So we can use a scalar equation of the plane using B cross n as our normal vector of the plane, which we are looking for.
The plane here, right? And we want to find the plane, the normal plane. What is it? Now, we are going to look at N and B. Okay? Which determines a plane. So I am going to do it. Skip 0. So what is it?
One zero zero or negative 100.
It should be this one.
Direction doesn't matter.
The t at 0. And this is I. Now let's check it. So we have ijk. N is 0, 1, 0. B is 0, 0, 1. And then you multiply like this, you have I, and the rest are all equal to 0. So this is I. Okay. So what are we going to get? So the plane is actually the y-set plane. Therefore, normal plane is just the y-set plane, right?
Sir,
Yes.
can you explain like why you took the cross product of the normal vector and the binomial vector?
I think that's the definition that we defined last time.
Okay, so that's in the definition from last time?
Yeah.
Okay.
Finally, we have to find the osculating plane. So how to do it? The osculating plane is obtained by looking at T cross N. And a student actually said that this is something like a tangent plane, but let's see. What is T? So again, we have IJK. And P is 1, 0, 0. And N is 0, 1, 0. So it's quite counterintuitive. You see that a normal plane is not something like a perpendicular plane. So we have this. And then we multiply like this. So we have K. And that's it. Yeah, we have K. So the plane is the XY plane. Therefore, the osculating plane is the XY plane. Osculating. is the XY plane. And last time, I told you the intuition. The osculating plane to a vector value function at a point comes closest to containing a portion of the curve at the curve. Now, in this case, the XY plane contains the complete curve. Right? So it certainly comes closest to containing a portion of the curve at the origin. Okay. So it's not the tangent plane, it's the plane that comes closest to containing the curve. That's what osculating means. It has a romantic meaning also, which I'm not going to tell you. Okay. Well, it's in the book. You can have a look at it. Okay, so we stop here. Yeah. So next time, we are going to chapter 14. All right?
Thanks, sir.
Okay. Okay,
Have a good day, Professor.
so see you on Wednesday.